Hey everyone, in this video I'm going to demonstrate how you can use u-Substitution to factor various polynomials. So we have two different examples here. In my first example on the left, you can see that we have an expression to factor, and in this expression we have this 3x minus 1 we can see is kind of like showing up in multiple places. So here it's almost like we have 3x minus 1 instead of just having an x. And in our second example, we have x to the fourth and we have x squared. So you'll notice that we have even exponents on every term in the second example. So let's start with this first example. If I have an expression that's repeated throughout my problem, such as 3x minus 1, and I notice that it's almost like I have a factoring problem with an expression put into it. So what I'm going to do is I'm going to say, let u equal 3x minus 1. Let u equal 3x minus 1. What that's going to allow me to do is that's going to allow me to rewrite my expression and focus just on everything else. So if I let u equal 3x minus 1, I can replace all of those 3x minus 1s with a u. And you can see that my problem looks a lot simpler now. My problem has become u squared plus 7u plus 12. It's important that I record what u equals, because later on, I'm going to want to put this back in terms of x. But using that u-Substitution, I've made my problem simpler. I can just focus on the frame around the 3x minus 1, and I can factor this as if it's algebra 1. So remember, we're looking for two numbers that multiply to 12 and add to 7. If I do that, I could realize that I'm looking for 3 and 4. So I could see that this problem factors to u plus 3 and u plus 4. However, my original expression was not in terms of u. So I'm not finished at this point just because I factored this simpler thing. Now that I've got it factored, I want to say, okay, I originally set u equal to 3x minus 1, so I'm going to rewrite this expression. I'm going to put the 3x minus 1 back in and see what I've got. So if all of my u's become a 3x minus 1, then I have this nice guy here, 3x minus 1 plus 3, 3x minus 1 plus 4, and now we can see at this point we have some like terms within our factors that we could combine. So I could combine like terms in the first factor and say, okay, negative 1 plus 3, that gives me 2. So my first factor is 3x plus 2. In my second factor, 3x minus 1 plus 4, negative 1 plus 4 is positive 3. So I could say 3x plus 3. At this point, I have my expression shown as a product of two linear factors. This is okay, but if we want to be really precise and say factor completely, you might notice that my second factor has a GCF. Both of those terms have a 3 in them. So I could, if I wanted to, take this even one step farther and say, okay, I could factor a 3 out of that second binomial. That leaves me with just x plus 1. And then to make things kind of more standard, I'm going to put that constant 3 in front, or not constant, coefficient 3 in front. And this would be my completely factored form of the problem I began with. So 3x minus 1 squared plus 7 3x minus 1 plus 12 is equivalent to 3 times 3x plus 2 times x plus 1. And you could check that by ensuring that they have all of the same solutions as each other. So that's how we can apply u-Substitution if we have an expression that we see repeated throughout our problem in parentheses, such as 3x minus 1. But I can also leverage this tool if I have In particular, if I have even exponents, such as x to the 4th, x squared, x to the 6th, x to the 8th, by using my exponent properties. So if I want to use u-substitution in this second problem, what I want to notice is I want to remind myself that x squared squared is x to the 4th. That's going to be useful for me. So over here, what I'm going to do is I'm going to say, let's let u equal x squared. If u equals x squared, I can rewrite this problem as x squared squared. Right? X squared squared would be x to the 4th minus 9 times x squared plus 20. And now if I'm doing my u-substitution, let's actually move this down here. If I'm doing my u-substitution, then I can rewrite this as u squared minus 9u plus 20, because I've defined u as equaling x squared. So you can see in this problem, using u-substitution allows me to work with smaller exponents. I had all these large even exponents like x to the 4th, x squared. Using u-substitution lets me work with u squared and u, which is a little simpler, and then deal with my x squared at the end. So if I factor this guy, I'm looking for two numbers that multiply to 20 and add to -9. So that would be u minus 4 and u minus 5. And now that I factored it, I'm going to put my x squared back in where I had my u's. So everywhere I had u, since I've defined u as being x squared, I'm going to put that x squared back in and see if there's anything else I could do. At this point, if we're factoring completely, we always want to ask ourselves, is there anything else I could do to take this further? So looking at these, what you might notice is that my first binomial is a difference of perfect squares. X squared and 4 are both perfect squares. My second binomial is a difference, but it's not a difference of perfect squares because 5 is not a perfect square. So I am going to factor x squared minus 4 into x plus 2, x minus 2, my x squared minus 5, since those are not perfect squares, will just stay how it is. So if I'm factoring over the integers, then this would be my completely factored form. I've used my u-substitution to deal with the x to the 4th. I've gotten my x squared minus 4, x squared minus 5, and then I did my difference of squares where it was relevant. I've got my completely factored form. So two different looking problems, but I can use a similar strategy with this u-substitution to make both of them a little simpler in the interim steps. And then after that simple step, put my definition of u back in to finish the problem out. Notice that my final answer is always back in terms of x. So the u substitution happens during the problem, but by the end of the problem, I've put it back in terms of the original variable. So my final third example here is x to the 8th minus y to the 8th. A common place you'll see this is differences of squares are very important, right? So recall that a squared minus b squared, anytime we have two perfect squares, we can factor that as a plus b, a minus b. So you can apply this concept of u-substitution to anytime you see a difference of something that is not that is a square but has a higher exponent. So recall that x to the 8th is the same as x to the 4th squared. Y to the 8th is the same as y to the 4th squared. So we can rewrite this. Even if I'm not using my u's, I could use the same idea. I could say, okay, this is like x to the 4th squared minus y to the 4th squared. Then I can apply my difference of squares formula from the purple. I can say, therefore, this is x to the 4th minus y to the fourth times x to the fourth plus y to the fourth. So I've just done a difference of squares, except I'm doing it with higher exponents. And then I can keep going, but I can only keep going with the binomial that is a difference. X to the fourth plus y to the fourth is not a difference of squares because it's not a difference. I have addition going on. But over here, I have a difference of squares once again. So I could notice that, okay, x to the fourth is equal to x squared squared. Y to the fourth is equal to y squared squared. So I could split this guy into x squared minus y squared times x squared plus y squared. This guy over here, it's addition, so we can't take it any further. And I'm just going to leave it all in black so that we know that that piece is already kind of complete. So now I've gotten this into three factors. Two of them have addition, so there's nothing else there's no GCF, I can't take them any farther, but I keep having this difference of squares going on. So I'm going to keep splitting up my differences of squares until I can't continue. X squared minus y squared, I know, is x plus y and x minus y multiplied together. So once again, I have a difference of squares. But my factors that were not differences of squares are just chilling. They're finished. At this point, I've exhausted my differences of squares. So I started with a difference of 8 of x to the 8th and y to the 8th. I just kept applying my difference of squares formula using a concept almost like u-substitution, even though I didn't even bother to use the u. And I ended up with this fully factored form that has 4 different binomials. Some of them have x squareds, some of them have x to the fourth, but none of them can be factored any further. So this is my completely factored version of x to the 8th, y to the 8th. So again, this is kind of a special example of substitution. It's applying it to a square inside a square inside a square inside a square. But the more common factoring by u-substitution examples would be something like what you see up here above, at least if you're doing the algebra 2 regents. Either a expression inside of something factorable, such as 3x minus 1, or a place where you could use x to the fourth, rewrite it as x squared.